Okay, before we get started, um, there's a mini lesson here at the beginning in getting things wrong. So, recording this, I've already done all this work, right? I recorded this once already. And then I realized that I had written the problem down incorrectly. Completely incorrectly. Mixed up two numbers. And so when I was looking for my solution, right, because we're going to be doing rational root theorem, as though we're checking with synthetic division, I got here and I was like, wait a minute, I think I should have found a root by now. And then I looked at the problem and I was like, wait, yes, I should have found a root by now. What's going on? Okay. I got really frustrated because I made a mistake, and it meant that I had to do all this meaningless work, which is super typical for these problems. But that doesn't mean we give up. We're going to go back. I got to do it again, right? Just because we make a mistake doesn't mean we give up. So that's my mini lesson before we start the actual thing about math. Sometimes the math can feel like tedious and frustrating. Um, that's okay. You just have to learn how to deal with those emotions, internalize and externalize them. So what we're actually doing is we're doing the rational root theorem continued. Specifically today, we're going to look at where q does not equal 1. So if you remember back to our last class period, we talked about the rational root theorem. Rational root theorem just says that, the solutions for a polynomial are going to be x, where we divide p and q, and this is the factors of the last number divided by factors of the first number. And last class, our first number, our leading coefficient, was 1. And here, our leading coefficient does not equal 1. It's all the same stuff, except two things are gonna happen. We're gonna get fractions, and we're gonna use them in our synthetic division. Okay. So, by way of example, 3x cubed plus 2x squared minus 23x minus 30. And if I wrote it down wrong this time, well, we'll just figure it out. We'll keep going. Maybe not. So step 1 is the same. List out all combinations of p divided by q. All of them. There's going to be even more now, though, because this is 3 and not 1. There'll be some duplicates that we ignore, or we'll cross them out. I'll show you. Because when the fractions divide, we're going to get some repeat numbers. That doesn't mean that there's a multiplicity there. It just means that's still a possibility. We don't need to check it twice. So x is plus or minus. Factors could be positive or negative. And we're going to start small and then end with larger numbers. So 1 over 1. All of these first set is going to be divided by 1. We're going to do the 3 can be divided by 1, so 1's a factor of 3. We're going to start with 1 on the bottom for all of these. And then the top of our fraction, p and q, is going to be the factors of 30. We start with the small numbers, work our way to the big numbers. So we can divide 30 by 2, by 3, not by 4, but by 5, by 6, And now I've crossed kind of the halfway point. 5 times 6 is 30, and 6 times 5 is 30. There's no 7. The next number is going to be 10 times 3. So our next number is 10. And then 15 to go with the 2. And then 30 to go with the 1. Okay. Then we also need all the numbers that have a 3 on the bottom. So all these same factors, p, that multiply to make the 30, except this time we're going to divide them by 3. So 1 over 3, 2 over 3, 3 over 3, oh, plus or minuses, sorry. Plus or minus 5 over 3, plus or minus 6 over 3, plus or minus 10 over 3, plus or minus 15 over 3, plus or minus 30 over 3. Oh, there we go, sorry. 30 over 3. Now, this is what I was talking about. Some of these fractions simplify and they show up as these things up here. So like we don't need to check 3 over 3 because that's just 1. We don't need to check 6 over 3 because that's just 2. We do need to check 10 over, well, we might need to check 10 over 3. 15 over 3 simplifies to be this 5, so we don't need that. And then 30 over 3 simplifies to be 10, and so we don't need that. And we're just going to check them. Now, normally I would just check all the integers for a couple reasons. The synthetic division is easier. It's more likely that we're going to find one with the integers. Well, I don't know if that's strictly true. But the synthetic division is easier. And so normally I would just go through the top row, even though we do get fractions. Okay. It's likely that the big numbers aren't going to be factors. Partially this is because we have a 3 here, and so this is going to be pretty big, and it's unlikely that it's going to even out. Now it might, but here's the thing. If 30 is a factor of this, then that means that 1 is a factor too, or as well. Because we have 3 solutions, this is x cubed, and whatever those 3 solutions are have to multiply to make this 30. So if our solution is 30, that means the other 2 solutions are either imaginary, which is possible, or they're 1. They're not going to be any of the other numbers. Okay, so we start at the small numbers because it's likely that it's not 30, and it's more likely that it's down here in these lower numbers. Okay. Now, like I said, normally I would start with the green ones. We're going to do the fractions because I want to show you the fractional synthetic division. Okay, so step 2 is just check the synthetic division, just like last time. It doesn't actually matter where you start that much. You could just pick 10/3 at random. You could just pick one. You could do any of them. You don't have to do them in order. It doesn't actually matter what order you do them in. Okay, so we're going to do the synthetic division. We're going to start with 1/3. And we're going to use these coefficients. So 3, 2, negative 23, negative 30. Okay. Now, this works the same way that the other synthetic division does, except this time we're multiplying by 1/3. So we add down and then multiply diagonally. Add the 3 down, multiply 3 times 1/3, or what's 3 divided by 3? We get a 1. So this becomes 3 times a third, that's 1 again. This becomes negative 22. Negative 22 divided by 3. This is not going to equal 0. Now this is a weird fraction, and we could do the subtraction or the addition here and figure out what this combines to make. But if it's not 0, we don't actually care what it is. So I'm not going to use it. I'm not going to use that. I'm not going to try and figure this out when I know that it won't add to be 0. This number has to be 30 for this to be equal to 0 and be a factor. So I don't need to finish the problem. We just check the next number. So we multiply. 3, oh no, add first, 3. Multiply, we get -1. We add, we get 1. We multiply, we get -1/3. We're going to add these together, and then we're going to multiply it by 1/3, and that's not going to give us 30. Right, if we're multiplying by 1/3, and we need this to be 30 so that this can be 0, these need to add to make like 90. So this isn't going to equal 0. So don't finish the synthetic division problem. If you know it's not going to get to 0, and it's a lot more obvious with the fractions than the integer numbers, but if you know it's not going to equal 0, then don't keep doing it. So then our next number on our list, 2/3. We're going to add down 3 times 2/3 is 2. We get a 4 times 2/3 is 8/3. This is going to add to be some fraction that doesn't simplify. And then we're going to multiply it by 2/3, which is not going to simplify. And so this is not going to equal 0 either. So then we check -2/3. 3, 2, -23, -30. So we're going to add down 3 times -2/3 gives me -2. This is going to make a 0. And then we multiply, we get 0, -23. We multiply, that's a 46/3. Doesn't simplify. This isn't going to add to be 0. I think the fractions are actually easier than the integers sometimes, because once we know that it doesn't, I mean, it's the same with the integers. Once you know that it's not going to add to 0, you don't need to finish the problem. -2/3. All right, so 5/3. 5/3, we got 3, 2, -23, and -30. So we add down, multiply, we get 5. Add, we get 7. 35/3. This doesn't divide evenly, and when we add it, it's not going to divide evenly, and then when we multiply it, it's not going to divide evenly. This isn't going to equal 0. Right, we need to get 30 right here for this to work. And so when we add these together and multiply by 5/3, we're not going to get 30. We're going to get something divided by 9. So -5/3. 3, 2, -23, -30. So 3 times -5/3 is -5. We add this, we get a 3 times -5/3, -5. Yep. -28. Wait a minute. Did I mess up again? Yes, I did. I was like, wait a minute. So this needs to be a negative. This is a -5. When we multiply it, the negatives cancel. This becomes a positive, and we get an 18. I was like, okay. Gotta be careful with our negatives. And then we multiply this. Multiply these. Divide this by 3. We get 6 times 5 makes a 30. We get a 0. Almost a disaster again. So what does that mean? Well, that means that negative 5/3 is a solution. And we talked about this a little bit, but we can write this as step 3 here. Step 3 is going to be fully solve this. We talked about this a little bit. I'm going to write this in a weird way first. So x opposite of this plus 5/3. Now that is not how we're going to write this when we're done. We're going to write this as integer stuff. But for now, that's the opposite of this negative 5/3. If we add 5/3 to negative 5/3, we get 0. So it's fine for now. And then we get 3x squared minus a 3x minus an 18. And that's all going to equal 0. Now here's where the issue comes. See how these are all 3s? We have a greatest common factor of 3. I'm going to factor that out, and I'm going to multiply this thing by 3. So 3 times x plus 5/3 times x squared minus an x minus 6. A couple things are going to happen. This is an easier quadratic to factor. It's just smaller numbers, it's easier. This, when we multiply, we get 3x. 5/3 times 3 is 5. And so we get this. Now we're not done because we have to fully solve this thing. But this is where the negative 5/3 comes from. This is what fully factored is going to look like. 3x plus 5. So I took the 3 out of here. Greatest common factor of 3. We could leave it like this, but we like integers instead of fractions. They're easier to look at it. They're prettier. And so we just distributed the 3. We multiplied it times the x, and we multiplied it times the 5/3 to get 5. Okay? I'm out of space, so I'm going to need to move this to another paper. But we need to fully factor this to find all 3 of our solutions. Find all 3 of our solutions. Okay, so we had 3x plus 5 times x squared minus x minus 6 equals 0. X squared minus x minus 6. A is, this is a quadratic, so we're going to use the Xbox method. A is 1, B is -1, C is -6. We need 2 numbers that multiply to make -6, add to make -1. Well, I'm pretty sure that's going to be a 3 and a 2, and the bigger one needs to be negative to make this one a negative. Since A is 1 here for our Xbox method, we don't need the box. You could fill this out and do it with the -3x and the 2x, and it will work. Or you just use the -3 and the 2. So we get 3x plus 5 times x minus 3 times x plus 2 equals 0. And so our solutions are the negative 5/3 that we found at the beginning, 3, and -2. Now, if you went through the integers at the beginning and checked those, you're probably going to find -2 first. And then you would factor the quadratic that comes from multiplying these. Okay, which might be easier than finding the 5/3 first. Not because you have to do less synthetic division, but just because you're working with integers. So what I'm going to do is I'm going to pretend I did that first for this same problem. So we're going to do the synthetic division for -2 since I know it's a solution. 3, 2, -23, and -30. We're solving the same problem again, so we're going to get the same answers, but I want to do this quadratic factoring here with the Xbox method when we have an a value that's not 1. So we're going to add down, we're going to multiply, we get -6, -4, multiply, we get 8, -15, multiply, we get 30, and we get 0. And so when we do x minus 2, we get x plus 2 times, x equals -2, so we get x plus 2. 3x squared minus 4x minus 15. Now there's no greatest common factor here. We're going to factor this using the Xbox method. So a is 3, b is -4, c is -15. Numbers that multiply to make -45, right? It's AC, and add to make -4. Well, it's going to be 9 and 5, I think. I did that pretty fast in my head, but just check what numbers multiply to make 45, add to make -4, go through 1 and 45, 15 and 3, until you get 9 and 5, right? And this one's negative. So the answer, right, we already know the answer. It's not my x minus 9 and x plus 5. We need to put it in a box. So it's this box. It's a 3x squared, a -15, a -9x, and a 5x. And so we get 5, -3, get a 3x this way, and we get an x. And so our final answer is x plus 2 times 3x plus 5 times x minus 3. This is probably easier than doing the fractional synthetic division, right? You still have to check 1 and all the 2's before you find 0, but it's probably easier than the fractional synthetic division. You just have to do a Xbox factoring for the quadratic when a doesn't equal 1. And when a isn't 1, we have to use the box. We get the same solutions. X is -2, -5/3, and 3. But I think it's maybe easier this way. Okay. Let's do one more. And I'll do it finding the integers first instead of using the fractions. But we still need to list them all out. Still need to list them all out. And I'm for sure going to run out of room here. 2x cubed plus 7x squared minus 7x minus a 12. Okay, so step 1, just list everything out. Well, x is going to be all the factors of 12 divided by all the factors of 2. So we start with 1. 1 over 1. We can divide 12 by 2. We can divide 12 by 3. We can divide 12 by 4. Divide 12 by 6. 7, 8, 9, 10, 11, 12. Those are all the factors of 12. 1, 2, 3, 4, 6, and 12. And now, because this is a 2 here, we're going to do all these same numbers, except we're going to divide them by 2. So plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 3 over 2, plus or minus 4 over 2, plus or minus 6 over 2, and plus or minus 12 over 2. And there are repeats, right? 12 over 2 divides to make this 6. We don't need to check that one because it's right here. 6 over 2 divides to make the 3. 4 over 2 divides to make the 2. 3 over 2, that's just a fraction. And 2 over 2 divides to make the 1. So we don't have to check those ones. Here there are only the 2 fractions. And I said we were going to check the integers, but now I'm looking at it and there's only 2 fractional options. And because there's a 2 here, and there's not a common factor, a greatest common factor, like I can't factor 2 out of all these numbers, it's almost guaranteed, it's guaranteed that one of these is going to be one of the factors, one of the solutions. Almost. I'm pretty sure. Yeah. One of those has to be it. Which narrows it down a lot. It's a lot easier to check these 2 numbers than to check all of those when I know there's going to be a solution here. And once I find one, then I can use quadratic factoring, which is easier than the synthetic division stuff, instead of checking all of them. Does that make sense why? The reason is we have to cancel out this 2 when we substitute in. And I know what factors look like. If we're saying this is a factorable function, not all of them are factorable, but if it is factorable, then the solutions, the numbers in the parentheses at the end, something times something times something, there's 3 of them because it's x cubed. One of these has to be like a 2x plus or minus something, because the rest of these are just going to be x's. To get this 2x cubed, we have to multiply a 2x times an x times an x to get 2x cubed, which means one of these is going to be 2x plus 1 or 2x plus 3. Don't know which. Okay, so that's not like a theorem or something. That's just a process of understanding how the factors multiply back to make our polynomial. And knowing, okay, if I have a 2x cubed here and it's factorable and there's no greatest common factor, that means that my solutions have to be a half or 3 halves. So I said I was going to check the integers, but I'm going to check the fractions because there's less of them. So step 2. Positive half into 2, 7, negative 7, and negative 12. So we're going to add here, multiply by a half, we get 1, which makes an 8. Multiply, we get 4. This makes a negative 3. Oh, that doesn't divide evenly by 2. So we get negative 3 halves, and this isn't going to make 0, so it's not 1 half. Let's check negative half. 2, 7, negative 7, negative 12. Add, multiply, get negative 1, we get 6. We multiply that, we get negative 3. This makes a negative 10. We multiply by negative 1 half, we get 5. And negative 7 does not equal 0. Well, that means, since we said it has to be one of these ones that divides by 2, it's going to have to be plus or minus 3 halves. Two, 7, negative 7, negative 12. So we add down, multiply, we get 3, we get 10. Multiply, we get 30 over 2, that's a 15. This subtracts to make 8 multiply, divide by 2. 8 divided by 2 is 4 times 3 gives us a 12, and we get 0. And so this does equal 0, which is good. That's what we're looking for. So that means that we get 3 halves. Well, that's going to equal x. But our factorization is going to be x minus the 3 halves times 2x squared plus 10x plus an 8. And you'll notice there's a greatest common factor here that wasn't in our original problem. That's because we have this divide by 2. So we're going to fix this thing by factoring out that greatest common factor. I'm doing x minus 3 halves because when we substitute in 3 halves here, 3 halves minus 3 halves makes a 0. We're just using the opposite of whatever this number is. And then we're using the coefficients from our synthetic division to write our next polynomial. And we got to fix this because it's got a greatest common factor. So x minus 3 over 2 times 2x squared plus 10x plus an 8. This is step 3, which is just solve all the way. So this has a greatest common factor of 2. Can divide each of those by 2, so I'm going to put the 2 here. X minus 3 over 2 times an x squared plus a 5x plus 4. And then we just distribute this 2 to both of these things. 2 times x makes a 2x minus 3 halves times 2 is 3. And then we need to solve this quadratic. So A is 1, B is 5, C is 4. Numbers that multiply to make 4, add to make 5. Well, don't forget, because it's not 2 and 2, those don't add to make 5. Don't forget that 1 times 4 makes 4. And so our answer is 2x minus 3. Well, our factored polynomial. We haven't found the solutions yet. X plus a 1 times x plus a 4 is equals 0. So our solutions are the 3 halves we found, a negative 1, and a negative 4. Gives us the coordinate points 3 halves, comma 0, negative 1, comma 0, negative 4, comma 0. Okay. Now it might have been faster to do the integers because negative 1. It's 1. We check 1 and then we check negative 1 and we would have found this. But I don't know if that would have been faster. There's no guarantee before we know the answer to what the answer will be. So these may have been 5 and 6, and it would have taken us a lot of checking before we found them. Okay. You could have checked 1, and then you would have gotten a quadratic where a is 2, and then you would have had to factor using the Xbox method. I want to do that as well. So imagine that we had known, or that we had done all the synthetic division work and found negative 1 first. So we did that into 2, 7, negative 7, negative 12. So imagine we were checking our integers first instead of the fractions. And so we get 2, negative 2, this is a 5, negative 5, this is a negative 12, positive 12, and 0. So this gives us, since we checked negative 1, x plus 1, right? We put a negative 1 in here, this turns into 0, so which is what we got at the end. And then 2x squared plus 5x minus 12. So we have to factor this using the Xbox method, but A is not 1, it's 2. So we have to check, we have to use the box. 5, C is negative 12. So we need two numbers that multiply to make AC, which is negative 24, add to make B, which is 5. I don't know. 8 and 3? Well, so 24 times 1, it's not that. 12 times 2, it's not that. Doesn't combine to make a 5. Yeah, 8 times 3. That'll make a 5. So it's 8 and 3, but the 3 is the negative number. Because when they add, they make a positive, so the bigger one's positive. So then we make a box. Stuff in the box adds to make this function here. So we have a 2x squared and a negative 12. That's these two things. And then these two add to make the 5x. So we have an 8x and a minus a 3x. And then we're just going to factor the common things out. So vertically here, take out a 2x, take out a minus 3, take out an x this way, take out a 4, and so we get x plus 1 times x plus 4 times 2x minus 3. 2x minus 3, x plus 4, x plus 1. You get the same solutions we got before. You get x equals negative 1, x equals negative 4, and x equals 2 over 3. Remember, to solve this, to find this number, we would take this thing, set it equal to 0, use our inverse operations from algebra 1. So you get 2x equals 3, divide by 2. We get x is the 2/3 that we had before. Okay. I need to replay that. That end was pretty quickly. But either way, okay, it's just possible that you're going to get fractional answers. You can either use synthetic division for fractionals, for fractional answers, fractional answers for fractions. You can use synthetic division with fractions, or you can use synthetic division with the integers like we have been, and use the full Xbox method where a is not going to be 1 to get an equation, and then solve for x and get a fractional answer. Okay, so we're still using the rational root theorem, especially because our original polynomial had no greatest common factor and no factoring by grouping. And so yeah, it wouldn't factor by grouping. And so we have to use the rational root theorem. And so then we list out all our guesses, check them, and then fully factor and solve. Okay. And that's our lesson on when our a value, our leading coefficient, is not 1.